All right, we are back, and we're still talking about sound. We've just been starting to talk about interference and some of the things and how that could affect things. And we want to look at that a little bit more. And we're going to try this little thing down at the bottom where I talk into the camera. We'll see how that works, or if it distracts me. I don't know if it distracts you. We'll see. All right, but we were looking at interference. We talked about if you have two waves, and these are transverse waves, where ripple go up and down like that. And where they meet right here, you can see that there are areas where there is no wave. Basically, it cancels out. We would say that they're out of phase, and one is going down while the other one's going up, and so they cancel each other out. Okay, and so there's no wave in between. Now, where there's two areas where both go down at the same time, one wave goes down, the other wave goes down, then it just even deeps down even farther and comes up. Okay. On the other hand, these areas where they're up, they're both, one wave is going up, the other wave is going up, and so they actually go way up. Okay. And so that would be in phase. When they're in phase, they're both going up or they're both going down. That magnifies the effect, and we say that is positive interference. If they're out of phase, one's going down and one's going up, and they cancel each other out, then that would be negative interference. And just like the names imply, you have positive and negative. Sometimes interference can be positive, sometimes it can be negative. Although sometimes positive interference can be positive, or positive interference can be a bad thing. Sometimes negative interference can be a good thing, positive thing, or sometimes it can be a bad thing depending what our goal is. If we want our sound to be louder, then interference is our enemy, or at least negative interference is, because it cancels it out. If you have want to cancel out sound, then it can be a good thing. Now, let's look at this real quick. Here's these are transverse waves. We talk about if they have positive interference when one's going up, the other one's going up, and then they end up both going up even more than the original, either wave by itself. That would be when they're in phase, they're in step, going up at the same time, going down at the same time, and therefore you have positive interference and it amplifies the effect. If you did that with sound waves, they're not actually up and down waves, the transverse waves, they're actually more compressional, where the atoms are being squeezed together, spread apart, squeezed together, spread apart. Now, you see on this one, if you have where they're close together already, and they hit another sound wave where they're being squeezed together, then the result is they're going to be really squeezed together. Okay? And in between the rarefactions where they spread apart, where two waves, rarefactions overlap, then the atoms are going to be really far spread apart. So this would be where they're in phase, and you're amplifying the effect. You have positive interference, and they're making louder sounds, and then so it would actually increase the volume, and that could be a good thing if you were like in an auditorium or something where you wanted there to be make it louder or amplify the sound. That's a good thing. Okay. On the other hand, if you have compressional waves like down here where they're out of phase, where this one is in a rarefaction, this one is in a compression, okay, and so one of them squeezing together, the other one spreading apart, so the result is nothing really. They cancel each other out. This would be out of phase, this would be negative interference, and so instead of hearing the sound, you wouldn't hear much sound at all because they actually cancel each other out. This one's close together, this one's far apart, this one's far apart, this one's close together, this one's close together, far apart, and they just kind of cancel each other out, and you don't hear much sound at all. Okay, and once again, depending if you want to hear sound or not, that can be good or bad. Now, when we talk about whether it's good or not, it depends what you want it for. It's kind of like friction. Friction can be bad, but it can be good sometimes too. Well, the same way with interference. It can be good or bad. If sounds overlap to make the sounds louder, like in an auditorium or a symphony hall or something like that, where you want to hear the sounds loudly, then that can be a good thing. And they can reinforce each other and make the sounds noisier. Now, what happens in noise-canceling headphones, okay, normally you have headphones, you're hearing the music come out through the speaker, it goes in your ear, but there's background noises, and those sound waves may interfere with the normal sound waves that you hear coming in. But if you put noise-canceling headphones, they actually have a little speaker out here, a microphone, that picks up the sound waves of outside, okay? And so say these are the outside sound waves coming like this, and then this little speaker would create opposite or anti-sound waves, if you will, just doing just the opposite, okay? So that when the outside sound waves are going up or going down, they're going up. When the outside sound waves are going up, they're going down, and they're out of phase, basically. And if they're out of phase, then you don't hear those sounds, okay? Now, the sound waves created by the headphone cancel out the ones on the outside. That's why they're called noise canceling. They cancel the outside noise. Now, if it's canceling sounds, though, it could also cancel sounds that you're hearing in the music if they were at the same frequency, okay? And so that is a problem. And so sometimes the quality might not be quite as well, but overall, the effect of canceling the outside noise is much better, and it makes it sound better overall. And also, generally, the outside noises tend to be of lower frequencies than the musical noises, and so their frequencies don't overlap very much, and so you don't have a lot of bad interference for the most part. It still gives you a much better overall sound than you would if you had the outside noise as you're trying to listen to your music. So that's kind of what noise canceling headphones do. They listen to the outside noise through a microphone, and they have a little speaker that produces the anti-wave or out of phase wavelengths that cancel out that outside noise so you don't hear it, and therefore you hear a much better sound of just the music that you want to hear. All right. Now, another function of interference is that of beats. In music, any time where we have here just two different tuning forks. Let's say you have different instruments playing in a band and so forth. They're going to have different sound waves and frequencies, and at times they're going to be destructive where they're canceling. Here you have a compression or rarefaction, okay? But sometimes they're going to be constructive. When they're constructive, it's going to sound louder. So you have places in the music that sound quieter, louder, quieter, louder, and so forth. There's some of the constructive ones that be louder, and that's basically what we call the beat, okay? It's just a mixture of destructive and constructive interference between the different instruments and sounds they make. So sometimes it's louder, and that's when it's constructive interference, and sometimes it's quieter. And that louder, quieter quality of the music is what gives it a beat. And according to my wife, I can't keep a beat, and so I don't, currently not very sensitive to that. But still, I've stepped on our toes a lot. We try to dance. So, but anyhow, that is what gives music its beat. It's the interference, both constructive and destructive, giving you louder and softer sounds when the sounds overlap in the different instruments. Now, when, say for example, we're shaking a rope here, so let's say it represents our wave. When the wave hits this and reflects, they move back to the same area, okay? And if we increase the frequency, then they come back. They can start overlapping with each other, the one being reflected coming back as well as this one. And sometimes these waves that are going both directions will be in phase with each other, which will increase it to go up, and sometimes it will be out of phase, which will cancel it out and make it flatter, okay? But eventually we may get what we call a standing wave, which means you have a standing pattern where you see this pattern, boom, 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 and these patterns are overlapping and they stay consistent, okay? And you have areas where the rope's not moving very much at all, and basically it's staying here. That would be called a node, N-O-D-E. Okay, like I node, that was what you'd call it, but there you go. Anyhow, so that's a node right there, N-O-D, where it touches. Now, where the farthest part is the opposite things happening, so that would be called the anti-node, and this would be considered a standing wave. And so this wave from here to here is only half of a wavelength. So from one node to the next node, it's just half a wavelength. From this node to the second node, where it's going back up again, that would be one wavelength. So basically, there's usually, in a standing wave, there would be two nodes per wavelength. All right? And there'd be two antinodes in between there also. Okay? And so that would be the example of a standing wave. This is just another picture of a standing wave. See how those bounces back, and as they come back, you end up with a standing wave. And you see the kind of the blur of the wave going back and forth, but you would need the node that stays in one place. This would be one wavelength right here. And once again, it's caused because of the interference of these reflected waves back and forth. Sometimes they're in phase and make it higher and lower. Sometimes they cancel each other out and make it in between. These type of waves are very common in musical instruments. Okay, so in musical instruments, when you pluck a string, it would produce standing waves if you looked along the length of the vibrating, say, a guitar string or the string inside of a piano. As it vibrates, you would see these nodes and antinodes. Now, if we were just sitting in one spot and we were sending out sound waves, we would say that the sound wave is going to spread out. Let's say this bug here is giving off a sound. These sound waves would go out and they would be spread the same distance apart, which means it has a certain frequency. All right. However, if the bug is not standing still, then as he's walking this direction, giving off new sound waves, since he's going the same direction, he's kind of catching up to the sound waves in front of him. And so you'll notice that these waves are closer together. Whereas these waves, as they're spreading away from him, he's also going away from them. So the waves keep getting farther and farther apart behind him. Okay? And so the waves in front of him have a high frequency. The ones behind him have a low frequency. High pitch, or high frequency has a high pitch. So you have a high pitch, and then these ones behind would be a lower pitch. If this was going past you, say you were at the TMS Motor Speedway, Texas Motor Speedway, and you hear the cars coming. When they come, they go, okay, can't do that again. You'll just have to replay it if you want it. But basically, that first sound you hear is as it's coming toward you. And then as it goes away from you, it's a lower pitch sound. But that's that difference in the sound of them. As they're coming toward you, they're higher pitched. As they go away from you, they are lower pitched, and that is called the Doppler effect, okay? Because as things move closer, the frequency gets lower and therefore get higher pitched. As things move away from you, then the sound waves get farther apart, have a lower frequency, and they have a lower pitch. Doppler effect can also be a result of sirens, things like that. As they're coming toward you, they're going to be higher pitched. As they go away from you, they're going to be lower pitched. Now, it doesn't really matter if you're moving toward the siren or if the siren's moving toward you. Either way, it's going to have the same general effect. Now, the same principles apply to weather radar. They shoot up radar. It hits the clouds and bounces back. And if the clouds are moving towards you, when they get bounced back, they're going to be bounced closer together and have a higher frequency. If they bounce going away from you, they're going to bounce back at a lower frequency. And because of this, then they can put it on the radar screen that we see on the weather, and they can show which clouds are moving which direction, and it tells us the motion of the clouds, and also the motion of winds in the cloud even, and that's how they help try to, the hook clouds and stuff that they use to diagnose if they think there's a possible tornado in an area, and things like that. Okay, and the last thing we're going to talk about with the Doppler effect is that we can use light coming from stars. If the stars are moving away from us, the light waves are going to be spread out farther apart and have a higher, so they're moving away from us, they're going to be farther apart, so they're going to have a low frequency. And so we tend to see the color would shift toward the low frequency, which is the red end of the spectrum. If they were coming closer to us, they would be getting closer together, and we would shift toward the ultraviolet or the blue end of the spectrum, and we would see that. And what happens is we in fact see the red shift, and so we believe that the universe is expanding because everything's being farther away and moving away from us in all directions. And so that's because of this basic Doppler shift, and so we end up seeing a red shift, the lower frequencies, because if they're moving away, their light rays have a lower frequency as they move away from us. Okay, so if the object in motion is less than the speed of the sound wave, they get closer together and farther apart behind, and that's the Doppler effect. Now, if you were to go just as fast as the wave, then you're staying up here, and the front of your waves all start overlapping, and this would be a wave barrier, okay? So there's like this barrier of waves that are piling up on top of each other. But if you actually go faster than the wave, so you send this first wave out, and you're actually above it when you send the next wave out, and faster and so forth, you're actually out here in front, and what you end up with these overlapping waves, they form kind of a V, okay? And this is called the bow wave, okay? And so it's kind of dragging behind off to the side. You could do this with a boat if you were going faster than the waves you're sending out in front of it, okay? And then if you really greatly, then it gets to this long, deep V here, okay? And so it's very strong and very pronounced. And it looks like we're going to have to go to the next video because we only have about 20 seconds or so to finish up, and I don't think I'm going to have time to do it on this one. So we're going to apply that to sound, and how would that affect and what would it sound like. Meet you on the next video in a few minutes. Thank you.